Okay, the second part this week we're going to talk about wind. Think of air. It moves. You can feel it in your face sometimes. You can watch leaves moving. Uh, and it pushes your aircraft around when you're up in the sky. So, or even on the ground sometimes if you have a strong enough wind. So, but air parcels move in 3 dimensions. We talk a lot about horizontal wind. So basically all wind east, west, north, south. If you're right at the ground level, that's horizontal wind. But that air parcel's possibly going up at the same time it's moving, or maybe it's trying to sink back down if it's up and above. So there's a total motion of the air parcel that you need to at least think about. That one air parcel that started here may wind up somewhere up in the sky at a whole different location. So that's why air is constantly in motion. So what causes air to move? Well, we deal with air in the sense of pressure gradient and other forces. Forces act on an air parcel to make it move. Force is basically mass times acceleration. Mass would be the number of molecules in an air parcel. Acceleration, how quickly all of a sudden it's jerking out there. And that would exert a force would be from that. So there are all kinds of forces that act on the atmospheric winds. A lot of times there's 3 basic forces that can really mess up and move things around and change. I think this is kind of complex, so rather than just talk about it like that, let's go back here just one thing for a second. Here it has pressure gradient force, Coriolis force, frictional force, and I'm going to add a 4th one in, centripetal force. So when you look at an air parcel, all 4 of those forces are acting on that air parcel. So with that, pressure gradient, think about it. If you had a tub of water here, a pipe, and the other tub was just barely a little bit in it, where is the water going to go? It's going to go down from the one tub into the other tub, filling it up. That's the pressure gradient. If you look at the atmosphere, you see highs and low pressures all over the weather map. Think of it as the atmosphere does not want any high or any low pressure. It's going to do anything in its power to get rid of those, what the atmosphere would think of as an anomaly. So anywhere there is high pressure, it's going to sink towards low pressure. It wants to make the atmosphere would love nothing better than to just be perfectly flat. You can't do it. There are many other things acting on it, like the sun, which we talked about last module. But that is your pressure gradient force. So the lines that you see on a weather map, the closer they are together, the greater those isobars are together, the more pressure gradient force there is, the better chance the wind's going to be stronger. Oh yeah, in the vertical, I talked about that. It changes very, very fast. So you have a tremendous pressure gradient in the vertical. So now that we've got that pressure, and remember, pressure gradient can be caused by density. The colder the air, the higher the pressure might be. Warmer the air, the less molecules might be there because they've been spread out, so a little bit less. So that might be a lower pressure. It doesn't always work that way, or they contrast with each other, but there's another force, Coriolis force. Coriolis force is one of the strange things about our planet. Our planet rotates. So, unfortunately, when it's rotating, if you think about it, if you lived up here by the North Pole, the planet is making this same loop as this does at the equator in exactly the same amount of time. So this person is not spinning around nearly as fast as the person down here at the equator. That's the Coriolis force. Coriolis force acts over time to change the direction like a ball would move so that it winds up curving. In the northern hemisphere, the Coriolis force always pushes molecules to the right of their flow. So if this flow was moving from west to east, that molecule is going to want to turn that parcel of air towards the equator. In the southern hemisphere, it's exactly the opposite. And those of you that live by the equator, believe it or not, have less Coriolis force than those of you that live near the North Pole. The further north you are, the greater the Coriolis force is. So now we've combined two. We've got Coriolis force and pressure gradient force. If you use those two together, we want to end up with what we call the geostrophic wind. It's a geostrophic balance. So there's a Coriolis force acting to the right of the wind and the pressure gradient acting towards the left. And they're in balance. So the air parcel just follows right along nice and smooth, right around these lines of isobars here. There's another problem though. If you ever look, the wind goes in a circle around the low pressure system. Well, that's the centripetal force that added to this. So there's another force that's constantly changing, that's making these air parcels go in a circle. And that centripetal force is the same force you feel when you go around a curve in a car. You're being held on that curve by that centripetal force. It's not letting you go flying out somewhere. So when they're all acting together, it makes the curved motion. Geostrophic is the straight wind, and the curved motion is from the centripetal force. So now that you've got the motions of the air, the closer, like I said, the closer together the isobars are, the stronger the winds. You can do it the same thing with contours. Friction adds one more component. Remember, if you're going over land and you have mountains, think about it. The air is trying to go around those mountains, up, down, over, however. The rougher the terrain, the more friction there is, and it's going to reduce and change the wind velocity. Just like a drag on that wind, that air parcels. So that's what friction does. Friction is going to cause convergence. Basically, it's causing the wind to turn towards low pressure because you have friction. Friction is not as much of a part the further up in the atmosphere you are. But the closer you are to the ground, the more friction you have. And they have other things that can produce vertical motions and changes in them. I wanted to talk about the hydrostatic equilibrium. It was mentioned in the last chapter. I think now's the time to talk about it. We talked about that tremendous pressure gradient force in the vertical, that you change pressures very quickly. So there is a very strong push with that pressure gradient force for an air parcel to go upwards to try to get rid of that pressure gradient force. But there's an equally strong push on that air parcel by gravity to pull it back down. That's the hydrostatic equilibrium. It's a balance between that pressure gradient in the vertical and the gravity pushing it down. So that is one of the many things that holds the air parcels in place. They can still move up and down, but they don't necessarily accelerate with the hydrostatic equilibrium. You may get strong winds up and down a mountain. Remember, gravity might even pull these winds down on the east side of the mountain, make them go a little faster. But gravity is another force. Tornadoes have a very strong pressure gradient force. But let's bring up just a surface map here. And if you were looking at winds on the surface map, see these barbs pointing down here? That's the direction of the wind. All meteorologists look at wind where it's coming from. So this is a northwest wind. So that's the direction the air has originated to the northwest of this site. And it moved in from there. If you're down here in Florida right now, for example, the air is coming out of the southwest. So the air originated in the tropics somewhere, off the Gulf of Mexico, pulling up moisture. So you can see where the air is coming from by looking at the barbs on a weather map. And the barbs, small barb would be only 5 knots of wind, a big barb, 10 knots of wind, and If you get a flag, it's 50 knots of wind. And you just add them up. That's how much wind is occurring at any one location. You can see there's not a lot of pressure gradient anywhere right now. This low just north of the Great Lakes is not that strong, 994 millibars. So look at it, the pressure gradient down here. Here's high pressure, 1016 millibars. So really, from Florida to that low, the pressure is only dropping, what, 22 millibars. It's 1,000 miles. So it's not dropping real fast. So we don't have a very tight pressure gradient here. No real strong winds. Now Laura obviously had a very strong pressure gradient. Looking at METARs, you've got to be able to read METARs again. So let's try to look at them now. Let's take a look at Beckley. Beckley's METAR. Here are your winds. The it's the very first group after Otto. It's almost always right there. So the very first three indicate the direction. So this thing is coming from 300 degrees. 300 degrees is northwest. So your wind is northwest at 9 knots, and there's gust. Okay, there's a difference between sustained wind and gust. Sustained wind is wind that you can average over 2 minutes. It's basically the wind speed over the 2 minutes. A gust is the maximum velocity that the wind parcel had during a 5-minute interval around this observation time of 51 Zulu. So 300 at 9, gusting to 16 knots. So now you've got the wind and you've got the pressure. And here were your temperature groups. So you're just really learning all about METARs right here. One final thing I wanted to look at is 700 millibars. We talked about the geostrophic wind. Here is a classic example of geostrophic wind. Notice how the wind is blowing right parallel to the contours. It's not cutting across them. If you looked here, the wind is cutting across the contours more. More friction, pulling it in towards lows and out away from the high pressure centers. So this is also centripetal force because it's going in a curved line instead of adding to it. So let me know if you have questions about things this week. Hopefully you understanding this perfectly. But if you don't, please don't hesitate to ask, and we'll talk to you later.